In 1952, Ray Bradbury published the short story A Sound of Thunder, a tale that would forever shape the way we think about the power of small actions. In it, a hunter named Eccles pays an enormous sum of $110,000 to travel back in time with a company called Time Safari Inc. This company specializes in taking adventurers millions of years into the past, allowing them to hunt the mighty Tyrannosaurus Rex. However, the company warns its clients that there are no guarantees, neither of safety nor of a successful return. The rules are strict. Every move in the past must follow precise instructions to prevent catastrophic effects on the future. The hunters arrive 60 million years in the past, where a levitating path keeps them 6 inches above the ground. They are forbidden to touch anything outside this path, as even the smallest disruption could cause ripples in the timeline. They are instructed to shoot only when given explicit permission. The company's system ensures that the T-Rex they target would have died naturally moments later, making their hunt a mere punctuation in time rather than a disruption. But Eccles, overcome with terror, abandons the hunt and runs back to the time machine, leaving the others to finish the job. When the group returns to the present, subtle but disturbing changes emerge. The air smells different. A sign on the wall features misspelled words. Eccles, examining his boots, discovers the cause of these anomalies: a single crushed butterfly. This tiny, seemingly insignificant death altered the course of history. Overcome with despair, Eccles realizes the enormity of his mistake and begs to undo it, but the damage is irreversible. Bradbury's story illustrates the butterfly effect, a concept that demonstrates how small changes in one system can have vast, unpredictable impacts in another. The term butterfly effect was coined in the 1950s by meteorologist Edward Lorenz. While developing a weather prediction model, Lorenz decided to round a number in his calculations to 3 significant digits instead of 6. He thought this minor change would make no real difference. Yet, when he returned to his experiment, he discovered a radically different outcome. A 0.03% variation had created a model that spiraled into wildly unexpected patterns over time. Lorenz's discovery revolutionized our understanding of systems, leading to the birth of chaos theory, a branch of mathematics focused on the unpredictable behavior of dynamic systems. This insight revealed a startling truth. Small, seemingly insignificant differences in initial conditions could lead to enormous changes over time. Lorenz's work also inspired the famous analogy of a butterfly flapping its wings in the Amazon, causing a storm in Europe. While the butterfly itself doesn't cause the storm, its tiny action represents an unpredictable starting point in a chain of events with massive consequences. This phenomenon, deterministic chaos, underscores the impossibility of perfect prediction without complete knowledge of every variable, a task far beyond human capability. Imagine this: predicting the orbit of a planet millions of years from now is simpler than forecasting Earth's weather a month ahead. Why? The former involves relatively stable, predictable factors, while the latter requires knowing the exact position, momentum, and interaction of every air molecule on the planet. A butterfly's wing beat introduces an imperceptible shift in atmospheric pressure, which compounds into larger and larger changes until it manifests as a major weather event. This idea that minuscule actions can create monumental outcomes extends beyond weather patterns. It applies to human history and personal choices. Consider pivotal moments like the Cuban Missile Crisis, where a single man's decision prevented nuclear war. In 1962, a Russian submarine misinterpreted depth charges from American ships as hostile attacks. The captain ordered a nuclear torpedo launch, convinced that World War III had already begun. Yet one officer, Vasily Arkhipov, dissented. His refusal to authorize the attacks stopped a chain reaction that could have turned the world into a nuclear wasteland. Arkhipov's single decision, like a butterfly's wing beat, altered the course of history. The butterfly effect also highlights the interconnectedness of our world. Every choice we make, no matter how small, sets off a cascade of consequences. Jonas Salk's discovery of the polio vaccine, for instance, didn't just save lives. It reshaped entire family trees, economies, and cultures. Without his breakthrough, humanity's trajectory would look unrecognizably different. Even in science, the butterfly effect challenges conventional models. Physics and mathematics often emphasize predictability, such as calculating planetary orbits or determining asteroid trajectories. Yet the butterfly effect reveals the fragility of these systems, exposing their dependence on initial conditions. Chaos isn't random. It's the natural evolution of complexity from tiny variations. To illustrate, consider the chaos game. Take a piece of paper, mark 3 points as A, B, and C, and place a random point in the middle. Now, repeatedly, mark a point halfway between your current position and one of the 3 points. Over time, what seems random begins to form a striking, intricate pattern, a fractal. This experiment shows how simple rules can create complex order, much like the universe itself. Ultimately, the butterfly effect forces us to confront the power of our actions. It's humbling to realize that even the smallest gesture can ripple through time and space, shaping outcomes we may never see. While we can't predict every consequence, we can recognize our interconnectedness and the profound impact of our choices. Every moment carries the weight of possibility, reminding us that change often begins with the smallest of steps.